Morning, everyone. Welcome back. I hope you had a nice evening and enjoyed San Diego's June gloom and overcast weather. We're going to start off today. A few things I want to point out again before. Make sure you filed your parking pass and claimed it. They are out in full force. So if you didn't get it in the email and parked, please double check it or come see me and we can sort it out. The other thing is, just because we have a lot of people who weren't able to make it yesterday and here today, if you can sign in just with your QR at some point today. The main two purposes for that are we're recording the talks and we're going to try and make them available. So there's a photo release. Can't guarantee you won't be in any of the shots and all that. But also there's an opt-in to have your contact info shared following the workshop. Basically, everyone who says, I'm cool with it, enters their name and email. I will distribute that list of names and emails afterwards, so if you wanted to follow up with anyone, you can easily do so. Another thing that kind of coincidentally coincides, one of the researchers who was here last week from RIT, I mentioned in my intro yesterday, they've developed this great database for quantum education and programs and everything across the United States. They're also looking to figure out some things about quantum sensing. So on your tables, there's some QR codes. If you're interested in, whether you're a researcher in the field or an educator, they have surveys and they want to conduct interviews and that. So they fill out an interest form. It would really help. It'd be useful. You can also get, I think, a $50 gift card should you do one of the interviews or something. So, sorry, what? Oh, yeah, and show of hands. Normally, what we'll do on one of the nights tonight, if you're interested in getting together with everyone for a dinner, there's Stone Brewery about a mile up the road. Sometimes we might need things. So if you would be coming tonight, if you want to join us, we just get a quick show of hands to see if we need a reservation or how many. So following the workshop, 10, 11, so 11 or 12. About a dozen. I think they'll have the hockey game on, which, we will leave early for that. It's game 3. First 2, we got free hockey with overtime. Second one was a gong show with just penalties. So who knows what we'll get tonight. Must-see TV. All right. Back to the formal agenda. We're going to start off today continuing with vapor cell sensing with Dr. Peter Schwindt from Sandia National Laboratories. He also has a setup that in the afternoon we'll be doing some hands-on stuff with. So thank you very much, Peter.
All right, thank you. Can everybody hear me okay? All right, yeah, so I'll be talking about magnetic field sensing with atoms. Specifically, we call them optically pumped magnetometers, or OPMs. And just clarify, this is David von Bach's setup, not my setup. It's he's coming from TeachSpin and we've adapted it to do some optically pumped magnetometry experiments. So really happy that David could join us here. Okay, so just let me start by giving a little bit of context for why we're doing atom-based sensing compared to other types of sensors. And so at the top here, I have some atom-based sensors. The CSAM I made this slide probably 20 years ago. And CSAM stands for chip-scale atomic magnetometers. And this is some very small devices, OPM devices that we built in NIST back in the early 2000s. And then another OPM type device is the MX optically pumped magnetometer. There's also something called a surf magnetometer. So these are all atom-based devices. And they have various field ranges over which they operate. And various levels of sensitivity. And am I getting a laser pointer here? Huh. Well, anyway, the red X is pointing out where the sensitivity is. And so the MX optically pumped magnetometer gets down to around 100 femtotesla per root hertz. And the surf magnetometers can get especially sensitive. They get down to like sub-femtotesla per root hertz. Okay. All right, thanks. Yeah, and then there's this field range over which they operate. And so a lot of these optically pumped magnetometers are designed to operate around Earth's field because that's what a lot of people want to measure is variations in the Earth's magnetic field. And so this is indicating the field range over which they operate. And then the surf magnetometers, you'll notice in particular, they don't go up to very large fields. So Earth's field is around here, but these surf magnetometers operate in a field range much below that, kind of maximum around nanotesla levels. Another spin precession-based magnetometer, but working on a nuclear spin, is this nuclear precession magnetometer. So I'm kind of quoting here commercial devices, and you'll notice their sensitivity isn't quite as good, but they operate well in the Earth's field, and often this kind of 100 picotesla level sensitivity is good enough for many applications. And then there are many other types of sensors out there. One big distinction between kind of these spin-based devices and all the other devices out there is that the spin-based devices, they will precess in a magnetic field no matter what the orientation is. And so that frequency of spin precession gives you a scalar measurement of the magnetic field, not a vector measurement. You know, obviously the magnetic field is a vector magnetic field, and often you want to know that vector information. And so all these other ones are really good for measuring that sort of vector information. So point out a couple of other ones. The search coils can be made very sensitive if you make them large. And search coil is just an inductive pickup coil, really. But it's an AC detector. It doesn't really measure DC magnetic fields. FluxGate's another popular one. And another quantum sensor here is the superconducting quantum interference device. This is a cryogenic superconducting device. These are also extremely sensitive and operate over a wide field range and are actually really good sensitive device and kind of our competition, if you will, for what kind of the best sensor do you want to use. And then there's a whole host of other vector sensors that are not nearly as sensitive as kind of these quantum-based devices. Another aspect of, or another specification you might care about is not only sensitivity, but also accuracy. How well do you know the absolute field strength? And that is another place where these quantum sensors shine, particularly these spin-based sensors. They're very accurate magnetometers. And in fact, you know, this is for a commercial nuclear spin, but if you make a helium-3 magnetometer, this accuracy can go way down much lower. And so nuclear spin can also be a very good magnetometer. Okay, so this is the outline of my talk. And so I'll start out by jumping into the basic physics of the OPMs, talk about the zero field surf OPM. Surf is spin exchange relaxation free, so I'll explain more about that. Talk briefly about the application that I work on in magnetometry, which is applying magnetic field sensing to magnetoencephalography. And I'll talk about kind of the most popular Earth field magnetometer configurations, which is the MZ and MX magnetometers. Another Bell-Bloom magnetometers, another variety. Then talk about some other topics. If I have time, get into some pulsed OPM spin squeezing, squeeze light, and talk about some more applications at the end. Don't want to cut too much into Andy's time here if I take too much time. So cut me off if you need to. Okay, so just start out with a very, very basic picture of an atom. And so we have a nucleus. We have some electrons around the nucleus. Here I'm just showing, I guess, the hydrogen atom with a single proton, a single electron. And so you can divide this up into energy levels. And then a photon comes along. You can promote this electron from the ground state to the excited state. And so that's and so this kind of resonant interaction is how we interact with the atoms when they're inside. Well, inside of here is a glass cell with a vapor of rubidium atoms inside of it. So that's kind of gives you the picture of we have a light source, we're sending light through the atoms, and then we're detecting the light afterwards. So the light interaction is very important. But what we're really using to measure the magnetic field is the electron spin. So it's a spin 1/2 particle, and it has two states, spin up, spin down, and there's also a nuclear spin, and these guys interact through the hyperfine interaction, and you can get a hyperfine ground state manifold that looks like this. And so there's an F = 0 state, an F = 1 state. We'll go into a bit more detail on that. But the important thing is the Zeeman effect. And how do these energy levels change with respect to a magnetic field? And so we've got a cute little animation here that shows these two stretched states, or these energy levels with larger angular momentum, azimuthal angular momentum. And these energy levels shift depending on the strength of the magnetic field. And so this energy splitting is what we're going after when we're trying to measure what the magnetic field is. Okay, so which atoms are used when we make an optically pumped magnetometer? So I've highlighted the 4 elements that are most commonly used for this. I mean, you can definitely build magnetometers out of other atoms, but these are the ones that have found their way into commercial devices. And so we have helium magnetometers, and these helium magnetometers actually promote one of the electrons up to a metastable state. So that one electron stays down in the n = 1 level, the other one goes to the n = 2, and that unpaired electron then in the n = 2 level we can use for magnetometry. These guys already have an unpaired electron in their ground state, and so these are the most common elements that we use. So it's potassium, rubidium, and cesium. Okay, so for completeness, I don't know if I want to go into all the details of this slide, but my assumption was that these slides would be distributed. Is that true? And so I wanted to have some of this information you could go look up for reference. But, you know, so we have spin angular momentum, nuclear angular momentum, and then the total angular momentum is the spin plus the nuclear angular momentum. So, and that's given by the symbol F. And so the hyperfine Hamiltonian is given by this expression here. You have the electron spin interacting with the magnetic field, the nuclear spin interacting with the magnetic field, and then the two spins interacting with each other. And some of these constants out here are quite important. We have the Bohr magneton, which governs how the interaction strength between the electron and the magnetic field. And then there's the electron G factor, which is about 2. And then you'll notice the nuclear magnetic moment is about 1,000 times weaker. And then if we go in and look at these hyperfine constants, here we have kind of the 4 main atoms here, which is potassium 40, rubidium 85, rubidium 87. No, this is 39. Why did I get 40 there? Huh. And yeah, potassium 40 is the rare low abundance fermion. And then cesium 133. So potassium 39 has a hyperfine splitting of 500 megahertz, but these other 3 guys are in the gigahertz range. Okay, and then when we're looking at the ground state, what governs the energy level splitting in the low field regime is given by this equation here, and then we can go look at then what the gyromagnetic ratio is for each one of these atoms, and so we've showing the G factor for each one of these guys, and so rubidium 87 and potassium 39 has about a 7 hertz per nanotesla gyromagnetic ratio. Rubidium 85, which we'll be looking at in this experiment on the table over here, has about a 4.7 hertz per nanotesla gyromagnetic ratio. And the cesium, because of its larger nuclear spin of 7/2, gets divided even further, and that's 3.5 hertz per nanotesla. Okay, so looking at the rubidium 87 ground state, so I have lots of slides on it, rubidium 87, because that's what I use almost exclusively in my magnetometers, even though over here we have a natural abundance cell, which has more 85 than 87. So this ground state looks like this. And so we have an F = 1 level, F = 2. And if we're going to have if we're going to make an atomic clock, I'm sure, Jan, you described this yesterday, but you probe the ground state hyperfine splitting on this 0-0 transition. But if you want to make a magnetometer, you're trying to look at the Zeeman splitting here in the presence of a magnetic field. And as I mentioned earlier, for 87, the gyromagnetic ratio is about 7 hertz per nanotesla. So we're trying to measure the splitting or the spin precession frequency derived from that splitting. Another concept I want to introduce is optical pumping. As I mentioned earlier, the light is a very important part of this interaction and how we measure the magnetic field. And so with optical pumping, say you have a ground state and an excited state. All your atoms are accumulated in the ground state and roughly equal population between these levels. But if you put on circular polarized light that carries some spin angular momentum, that'll drive transitions out of this state. And because of selection rules, this state is dark, and so it's not getting excited by the circular polarized photons. And so what that does is the atoms get excited up to this state, and when they decay down, they have a chance to go to either one of these states. But because you're constantly driving atoms out of this state, you accumulate your population over in this state. And so this is very important for preparing the spin state of the atoms. And if we think about the direction of the spin vectorially, we're generally trying to pump the atoms along the direction of the magnetic field. So the electron spins are aligned along the direction of the magnetic field. And that's kind of a spin preparation step that's always required in the optically pumped magnetometers. Optical pumping, right? That's why they're called optically pumped magnetometers. Okay, all right, so just put a few more details around the magnetometer concept here. So over here we have this glass cell, and inside we'd like to think about a bunch of randomly oriented spins associated with each one of these atoms. And then we put on our circularly polarized light, and that orients all these spins in a particular direction, aligned with the pump beam, or along the direction of the pump beam axis. And then if there's a magnetic field that's out of plane here, that'll cause the atoms to start to precess about the magnetic field. And so this could be like a very low field case where we're just getting some constant angle, or this could be a high field case where, say you instantaneously turn on a magnetic field, all these spins will start to precess very rapidly around the magnetic field. And then what we need to do is try to detect the angle of these spins. And there's a whole bunch of different ways to do that. I'm indicating one here where we have a probe beam that is linearly polarized and off-resonant. And so we're looking for the Faraday effect. And so when these spins are highly polarized, they will treat the index of refraction of right circular polarization and left circular polarization is different as the light propagates through the gas. And so that'll cause a rotation of the output polarization as it propagates through the gas. And so this is one way to measure the orientation of these spins. The other way, you can simply use this probe light that's going through, and you can just simply measure the amount of absorption. And so with this optical pumping here, because you're pumping to a dark state, the stretch state is a dark state. And so when all the spins are aligned, they're not absorbing light anymore. So all your light will transmit through. But if, say, you start to have some precession, and say if you have enough precession to tip the spins all the way back, pointing in the opposite direction, you'll have maximum absorption of the light. So that is another measure of the angle of these spins relative to the light. And so there's, yeah, a lot of different ways to make this all come together and make a magnetometer. Okay, so I put this slide in just for completeness. If you really want to capture all the effects in an optically pumped magnetometer, you need to do a density matrix model for the atomic vapor cell system. And this thing is really complicated. And if you really want to know all the details, talk to Jan Yu over there. I personally have never solved this equation. He has. So, but there's a number of terms here. So you have the hyperfine interaction, you have the Zeeman effect, you have spin exchange collisions. I'll talk about more later what spin exchange is. You also have spin destruction collisions. Talk about that some more. And then you'll have a term that describes the optical pumping. And then because these atoms are at room temperature or hotter, and they're in the gas phase, they're going to diffuse through the cell because we put a buffer gas in there to kind of limit their motion. And so we have to model this diffusion as well to really fully understand what's going on in the system. And this reference down here, if you want to dig into this, I don't know, 30-odd page paper, it'll tell you all about it. What is more typical is to simplify that density matrix into a block equation for the ground state. And so you have all the same terms, it's just simplified dramatically. And it also turns into, instead of a matrix equation, it turns into a vector equation. And so you have your atomic polarization P and your magnetic field. And so this cross product here describes how the atoms behave in the magnetic field. And so this is a lot like the precession of a top, right? That's why we call it spin precession, because the spins are rotating around the magnetic field, just like a top rotates around the gravity field. And then also we have our optical pumping, and we also have a vector associated with the direction of the optical pumping, S. And then also optical pumping contributes to depolarization of the atoms. We have a whole bunch of other depolarization effects we described with T1 and T2. It's describing some of these processes like spin exchange, spin destruction that I talked about earlier. And then we also have diffusion again. Yeah, so I think that's all I want to say here. And I'll be coming back to this slide as we change how we use this block equation depending on which magnetometer we're trying to model. Okay, and then the next thing before I jump into the surf magnetometer is just talk about the magnetic sensitivity limits. And the basics of magnetic sensitivity is, say, if you're trying to measure very precisely what the magnetic field is, you're going to do that measurement. There's going to be some noise associated with that measurement. And then there's also going to be, how does your signal change with magnetic field? So there's going to be some slope associated with this signal that you're trying to measure the magnetic field with. And so if we look at the atom shot noise or the spin projection noise limit, that's very simply given by this expression here. And so we have 1 over the gyromagnetic ratio times the square root of the number of atoms participating in measurement times their coherence time, and then times multiplied by the total measurement time. And so we get this 1 over root n scaling, which you would expect from kind of a statistical shot noise type measurement. And then we can improve the sensitivity by either increasing n or increasing T2, and so we work on both of these aspects to improve the sensitivity of the magnetometer. Yeah, but I gotta say, most optically pumped magnetometers, so this is old AM stands for atomic magnetometers, don't operate in this limit. You're most often, the fundamental limit you're limited by is the photon shot noise. And this is how much light is passing through the cell, and the counting statistics of detecting the light passing through the cell. And so that's also proportional to 1 over the square root of the number of photons. Okay, so let me get into the surf magnetometers here. And so the surf regime is a very interesting regime, and also very useful because it gives you very high sensitivity. And so T2 in magnetometers, particularly Earth field magnetometers operating kind of ambient environment magnetic field, is limited by spin exchange collisions. And so these are collisions where the atoms, say you have some atoms, you start out with atoms in this state, but as they decay, they kind of get distributed throughout all these states. And if they collide, the spin exchange collision conserves the overall total angular momentum between the two atoms, But they can flip hyperfine states because you're changing the spin orientation of the electron relative to the nuclear spin. And so I've kind of have some like loosey-goosey, hand-wavy type explanation to try to give you a flavor of what's going on with the spin exchange process here. And so say you have two atoms here, and this is in kind of the Earth field, high field regime here, and they can precess in a magnetic field, but then they'll have a spin exchange collision. So what happens when you have the spin exchange collisions? Well, perhaps one of these atoms will flip from the upper manifold down to the lower manifold, and you'll notice that how they're drawn, that these guys have opposite gyromagnetic ratio. That means the atoms in the F=1 state precess in the opposite direction. And so they start precessing in the opposite direction compared to the upper state, and they rapidly dephase. And so what that means is that if you take an ensemble average over your 10 to the 13 atoms that are participating in this measurement, the spinning or the overall polarization of the ensemble will decay very rapidly. However, if you're in the surf regime, you're in this unique position where the spin exchange collisions are happening much more frequently or much faster than the spin precession rate. So you're in this low field regime. And so I got an animation here to try to indicate what's going on with that. And so your atom starts to spin, then it undergoes a spin exchange collision, flips, goes back, flips back after another spin exchange collision. But what's happening is because you're not precessing very far, your precession between collisions is much, much less than a radian. You can kind of view this as all the spins in the ensemble locking together. And so the spin exchange is no longer a source of decoherence. And because you're flipping between these states, your spin precession rate is lower, but you're not decohering. So you maintain a very strong amount of polarization. And you can get kind of 2 orders of magnitude increase in T2 by going into the surf regime. And because of this lengthening of T2, you can get some record sensitivities. So the Morales group at Princeton has shown down to 160 attotesla per root hertz. And then the NIST group in Boulder showed in a 6 cubic millimeter volume, or maybe that's the volume of the cell, they can get down to 5 femtotesla per hertz. So in a very small volume, we're able to achieve a very high sensitivity. And just to give a sense of scale, just know that 5 femtotesla or 1 femtotesla is a very good sensitivity for magnetic field measurements. Okay. Some other aspects of the surf regime is, well, I mean, at low field, we're in the surf regime. At Earth field, we're not in the surf regime. So what's going on? How are we transitioning between these two regimes? And so if you do a density matrix analysis, we can't really use the Bloch equation to describe how we're transitioning between the surf and traditional magnetometers, not without some major modifications and approximations. But using density matrix analysis, you can do this. And so this expression was derived, I guess, back in the 70s by Will Happer. And it's a complex expression, kind of hard to understand, but it's describing both the line width and the spin precession rate. So both of the decoherence rate and the spin precession rate is affected by going to the surf regime. And so over here, here's a plot. So as we change the magnetic field, we can change the half width, half max of the resonance. That's and the relationship between T2 and the line width of the resonance is given here. And so from this, you can say, if we're going to reduce the line width or increase the coherence time by 2 orders of magnitude, that's going to give us an order of magnitude increase in sensitivity. And so that's really where all the excitement around the surf regime is this transition going from high field down to low field. And just point out, say, the rubidium relaxation cross sections. The spin exchange cross section is 2 times 10 to the minus 14 centimeters squared, whereas the spin destruction rate is around 1 times 10 to the minus 17 centimeters squared. So that's kind of this 3 orders of magnitude different in cross sections. Okay, and then, we don't want to do density matrix modeling. We want to use a block equation to describe what's going on. So how do we modify the block equation to describe what's going on in the surf regime? And that's basically done by adding this nuclear slowdown factor out in front of everything except for diffusion. And so this nuclear slowing down factor, if we plot this over here for different nuclear spins, so rubidium-87 operates or has an I equal 3/2 as a nuclear spin. And so you get kind of interesting form of the of this nuclear slowdown factor. And so if we plot that as a function of the atomic polarization, so this how far, if we got all the spins optically pumped in a particular direction, the nuclear slowdown factor, or the polarization is 1, and so we have these high polarization limits for the nuclear slowdown factor. And then if it's 0, there's no polarization in the ensemble, then the nuclear slowdown factor is this. And so the high polarization limit is equal to what we see also in the high field limit, whereas when you have low polarization, you have quite a modification of how the spins process. So what does this do to the gyromagnetic ratio? You can see in the high polarization, going from high polarization to lower polarization, you have a decrease in the gyromagnetic ratio. But this is only, a small diminution in the gyromagnetic ratio where you get, 2 orders of magnitude improvement in T2. So you don't care so much about that small change in gyromagnetic ratio for the sensitivity. Okay, here's another dense slide that I added a bunch of information to for your reference later. But I wanted to talk a little bit about the different relaxation processes in a vapor cell and how you might optimize a vapor cell to get the best, narrowest line width. And so maybe this lower plot is probably most relevant because what we want to do when we're making a vapor cell is decide how much buffer gas to put inside that vapor cell. Do you want just a torr? Do you want several atmospheres? What do you want? And so what we are attempting to do with buffer gas is we're trying to prevent collisions of the atoms with the cell walls. If an atom goes and sticks to a cell wall for a short amount of time, the spin information is completely scrambled and you lose all the polarization of your sample. So you want to limit that. You don't want to use a buffer gas-free cell. And but you don't want it too high because you have an alkali buffer gas spin destruction rate. And that's given by the density of the buffer gas times the cross-section times the velocity. And then you have this kind of strange correction factor out here with temperature. And so you can see here. So here's the blue line is the diffusion. And so as you add more and more buffer gas, you're reducing the amount of decoherence on the cell walls. The yellow line here is the result of the alkali buffer gas spin destruction cross sections, or spin destruction rate. And the green line here, independent of buffer gas pressure, is the alkali-alkali spin destruction. And so these are the alkali-alkali collisions. And that's given by this formula here. And so when you're trying to optimize the performance of the atoms inside of a vapor cell, you're trying to increase the buffer gas pressure to limit up to the point where you start to become dominated by these buffer gas collisions destroying the spin. And so you want to operate kind of at this minimum right here. And then in terms of temperature, you have the rubidium density is very dependent on temperature. And so as you increase the temperature, you'll see that the total relaxation rate, or the line width, will increase with temperature. So there's probably going to be some optimum here in temperature where you want to operate as well. And then just to get some of these cross sections here, there's a nice paper from the Morales group back around 2002 showing some of these cross sections for the different alkali atoms. And you'll notice the alkali-alkali, or the self-spin destruction cross-section here is best for potassium. So if you want the ultimate sensitivity in a surf magnetometer, you want to use potassium. But rubidium's not too bad, but cesium is starting to get worse. I often use rubidium because its vapor pressure is a lot higher than cesium. Oh, sorry, a lot higher than potassium. Cesium even has a higher vapor pressure, but this cross-section is a little large for trying to make a surf magnetometer. Okay, but you don't want to just optimize T2. You want to optimize all parameters in the system, and what we're really trying to optimize is the sensitivity. And so this is a plot that's very similar to what I showed on the previous plot, where we're plotting the line width as a function of the potassium density. They're using potassium in this paper from Romales, but here's the sensitivity. And so because as you're increasing the atom density, you're increasing the number of atoms participating in the measurement, but also as you go to higher and higher temperatures, you're going to be increasing T2 as well. And so at the highest temperatures, you're kind of flattening out the sensitivity because as the number of atoms go up, the spin coherence time is going down, and those cancel each other out. But there's some interesting properties of this plot that are relevant to the surf regime here, which is this dotted line here is just showing spin exchange. And so as you start to increase density, spin exchange starts to decohere more and more. But once you enter the surf regime, spin exchange is no longer a decoherence mechanism. And so spin exchange starts to go down like this. But then if you add in the spin destruction, between the alkali atoms, at some point that rate becomes significant and the spin exchange decoherence drops below that, and so then spin destruction starts to take over as your major decohering process. And then if you add in all the other different decoherence processes, you get this solid black line on top here, adding in diffusion and buffer gas spin destruction collisions. So trying to give a little bit of a flavor of how you optimize and how you get good sensitivity with the magnetometer. Okay, so let's talk about some of the signals that you can detect in a zero field magnetometer. Take our block equations, solve a steady state solution, so set the derivative equal to 0, and then what do you get? And you get some equations that look like this. And interestingly, in this zero field regime, you're not really doing a scalar measurement, you're actually doing a vector measurement, because you have all these different ways in which the individual vector components contribute to your spin polarization in the different directions. So Px would be in this direction here. Here's a little plot here. We're optically pumping along Z. And so what we're going to be doing in this device over here, for the most part, is optically pumping along Z. And so we're going to be looking at the zero field resonance in this system. But first, let me point out that if you're measuring in the x direction, which is what a lot of two-beam surf magnetometers do, you get this nice dispersive response to a Y magnetic field if that's the only field present. And so you can get this nice linear slope, and you can use this nice narrow linear slope to measure the magnetic field. If you're measuring in the Z direction, which is what I do in my magnetometers, you get kind of a Lorentzian shaped thing. This is not a perfect Lorentzian because it's actual data, not a calculation of this equation here, this PZ equation. But anyway, you get kind of a pseudo-Lorentzian shape. And as you scan the magnetic field in the Y direction in and out of the board, you get the Lorentzian shape. And then if you add some modulation in and out of the page, you can do some modulation spectroscopy type things to and phase-sensitive detection to turn this peak into a dispersible Lorentzian shape. And then once again, you have a very sensitive measure of the magnetic field. And then this is a video from my colleagues at NIST who are trying to show this process in a little more detail for measuring along the Z direction. And so you have the magnetometer or the glass vapor cell, which contains a bunch of atoms. All these atoms have spins associated with them. And then if we bring light in, we can orient these spins in a particular direction. So it's going to come in here. We have circularly polarized light that will align all these spins along the direction of the optical pumping axis. And then if a field comes along, that'll rotate the spins, or the spins will precess about that magnetic field. And that will decrease the amount of transmitted light. Because when it's not aligned with the axis, you get a lot of absorption. But when it is aligned, you get a lot of light doesn't get absorbed, you get transmission. And so as the magnetic field changes, you're changing the amount of light that's being transmitted through the atomic vapor cell. And that's the signal that we're using to determine what the magnetic field is. Okay, so now I'm going to zoom into the magnetometers that I build for magnetoencephalography. And it's based off this kind of the ideas that came out of this paper, but I put a little twist on it and used, there's two optical transitions in rubidium called the D1 or D2 transition that's determined by the fine structure of the rubidium-87 atom. And so we're going to do optical pumping on the D1 transition and probing along the D2 transition. The reason I want to use two different colors is I'm trying to build a single axis magnetometer to simplify the optical configuration of the device. So as described before, we use circularly polarized light to pump the atoms. And then we're going to co-propagate light at 780 nanometers that's linearly polarized to read out what the atoms are doing. And we're going to, again, use the Faraday effect to measure what the atoms are doing, the polarization rotation effect. How do we do this kind of dichroic dance, if you will? And so D1 light, we want it to be circularly polarized, so we have a multi-order wave plate that's just the right thickness to make it a quarter wave plate for D1 and a half wave plate for D2, so we can maintain linear polarization on 780. And then when we're detecting the light, we use an interference filter to only pass the 780 light, so we can measure the polarization rotation signal. And then finally, we add a magnetic field modulation, say in this case in and out of the board, and that defines the sensitive axis of the magnetometer. That defines the vector field component that we're going to measure. And then we do lock-in detection at this modulation frequency omega. Okay, so what do these signals look like? Pretty similar to what I showed before, but this cyan line is the basic magnetic resonance as you scan the magnetic field. And then once you add that, in our case, 1 kilohertz modulation, you add a lot of fuzz, but you still get this dispersive shape. But if you demodulate the red signal with a lock-in amplifier, then you get this blue signal. You get this very steep linear slope, and you can use that then to discriminate what the magnetic field is. Okay, so one thing you'll note is that there's a very limited magnetic field range over which you can measure. You know, if you go beyond like 10 nanotesla or so, you're getting into different parts of this lock-in amplifier signal, which is not particularly useful. And so this kind of shows that effect as you increase the magnetic field amplitude you're trying to measure, and then what is your output voltage out of your lock-in amplifier? It starts to roll over. However, you can do a closed loop measurement, and so say if you're trying to measure in the x direction here, then you can apply a feedback magnetic field to linearize and give you a larger magnetic field range over which to operate, and you're using these coils to always drive the magnetic field at the location of the atomic measurement to 0. So you're just trying to keep that at 0, and then use the output or the current going through these coils to give you a measure of the magnetic field. Okay, a little bit of history of surf magnetometers used for magnetoencephalography. Magnetoencephalography is the measurement of the magnetic fields produced by neurons firing in your brain. So if you get, say, about 10,000 neurons firing simultaneously in your brain, you have kind of 100 femtotesla or so signal just outside the surface of your scalp. And you can measure measure that to determine what is going on in the brain. And so this was first demonstrated with optically pumped magnetometers back in 2006 at Princeton. Our group was next back in 2010. We made a modularized sensor that brings light in through fiber. This measurement here was done with a very large vapor cell and free space beams coming in, so it was hard to imagine then how you would make full head coverage. And so we were working on fiber coupled sensors with a vapor cell right next to the head. And then with this concept, then you can think about, I can take multiples of these sensors and put them all over the head, and we get kind of full head coverage to see what's going on inside the brain. This made some very nice advancements in miniaturizing these devices, which is pretty exciting. And then Qspin in 2013 made some nice compact sensors that were used to measure the brain. And so in terms of these ultra compact sensors, it's probably the first measurement in this paper here that happened in 2013. Now there's companies that are selling these really small devices. And so this is showing one of these highly miniaturized surf magnetometers from Qspin. Here's I'd say more of a concept picture from Fieldline. They've evolved how they're actually doing this. But you can see a whole bunch of sensors placed over the head. And so these are two companies based out of the Boulder area. People coming out of the NIST group, which is also where I came from. It's kind of funny, all three of us are exploring MEG with magnetometers in different directions. And now there's been a lot of development of magnetometers over the last decade in China as well. And so there's more than one company that's trying to do surf magnetometers for magnetoencephalography. So our project, we are working now towards making a full head coverage array inside of a magnetically shielded room. And sorry, I just kind of pulled these slides, but I'll just point out this is a schematic of our device. We're trying to build a 4-channel device. So we bring the light in, we split the light into 4 different beams with a diffractive optical element, and it goes into kind of a large vapor cell here. And where the light interacts with the atoms in a particular region is where we're measuring the magnetic field. And so that's shown in a little bit more detail in this 3D picture here. So we have 4 beams coming in, and we're probing the magnetic field in these 4 different locations in the vapor cell. So light comes in on a fiber, goes through a polarizer, a lens to collimate the light. We have our special wave plate, and then the DOE spreads the light out. And then finally, we detect with this detection module. So it's a little kind of 2 photodetectors and a polarizing beam splitter cube, so we can measure this polarization rotation. Also point out that our vapor cell operates around 130 to 135 C. I think that's shown here. Yeah, so we kind of have this opposite problem of squids. Squids are kind of the gold standard for measuring what's going on in the brain. They operate at 4 Kelvin. We're operating at some 130 to 150 C. And so, but this is a heat problem is much easier to solve than the 4 Kelvin problem. And so with some fairly straightforward insulation, we're able to insulate the human subject from the high temperature vapor cell. All right, so here's a picture of our device. It's about this big. And here's some on-sensor coils that we use to apply modulation to define the sensitive axis of the magnetometer. And then I just point out, not only do you care about sensitivity, but you also care about the bandwidth of your measurement. And so here we're plotting the response of the magnetometer as a function of frequency. And so this device has a bandwidth of a 3 dB bandwidth of 90 hertz or so, 90 to 100 hertz. And we're also showing the cancellation with, if we subtract the signals from 2 adjacent channels, we can get some gradiometric cancellation. And so with these signals, we can suppress common mode signals by about a factor of 100. Looking at the sensitivity of the device, if we focus simply on the magnetometer, we're operating around 10 femtotesla per root hertz, but with the gradiometer, we can get down to around 5 femtotesla per root hertz. That is if we're subtracting adjacent channels in this 4-channel magnetometer. So that's good sensitivity if we're trying to measure these 100 femtotesla fields. Gradiometric signals are giving us a sensitivity sub 10 femtotesla. We can get decent signal to noise on these brain signals. Maybe I'll skip that one and just show some of the brain signals that we're able to measure. And so if we place several magnetometers on the side of the head, and let's focus on this guy over here. So AEF stands for auditory evoked response. So we put a beep in both ears and then measure the auditory cortex, which is just over the ear on both sides of the head. Then you're able to get some nice signals after you average 300 or so trials together. And so we're showing this peak, and that peak shows up about 100 milliseconds after the start of the tone in the person's ear. And then, since we're measuring in multiple locations, we can make a magnetic field map at the maximum amplitude peak and then say, okay, where is that magnetic field coming from inside the brain? And, oh, that's a bad example because this is the somatic sensory cortex. But anyway, this is showing that we can localize where things are happening inside the brain at one of these strong peaks for these different stimulations we're giving the subject. And and we're also comparing our localization relative to a squid system, a full head squid system, just to show that with the OPMs we can do the same sorts of localizations that's done with the more of a gold standard full head squid MEG system. Okay. All right. Wow, only got 20 minutes left. A lot to go through on the. Sorry, Andy, you're toast, man. But mainly, I want to get through these MZ and MX magnetometers, as they're the most common Earth field sensors. And so, as I'm sure you know, the Earth's magnetic field is given by the core of the Earth, and so we got this magnetic field coming around. But really, so you can use magnetometers to measure the magnetic field in space. That's frequently done with optically pumped magnetometers. But you also probably care most about what the magnetic field is on the surface of the Earth. And there's a whole host of applications for measuring what the magnetic field is at the surface of the Earth. But since we're moving away from zero field up to a more finite field in terms of our field measurements, we've got to think about the nonlinear nature of how these magnetic fields, or how these energy Zeeman levels split apart. And so if we take a look at the Hamiltonian for the ground state and diagonalize that, you get the Bright-Robbie formula that's shown here. And it can be simplified with this equation. And I have some plots, I think, here on the next slide that show how this all plays out. And so, yeah, all my older plots, all my minus signs went away. So where you see a square, it's a minus sign. But here we're plotting the magnetic field up to 1 Tesla. And so when we're down here in the lower field regime, this is called the anomalous Zeeman effect, where F is a good quantum number. And so when we're operating the Earth's magnetic field, we're down in this regime. But there's still there's a quadratic correction that we can use to really get a more precise measurement of the magnetic field at that range. At the high field regime, it's called the Paschen-Bach effect. But we're going to be focusing on what's going on down here, these kind of tens of microtesla range. So once again, we're going to be using the Bloch equation to model what's going on, staying away from that pesky density matrix equation. And then because we're at a finite field, the atoms, we have a pretty strong magnetic field, and the atoms are fairly rapidly spinning around the magnetic field. And so that means we're going to want to use something called the rotating wave approximation. Maybe that's already been mentioned, to go in a rotating frame, and we're going to rotate at the frequency that we're applying an RF field. So what we're going to be trying to do is say our optical pumping aligns the spins in this direction. We're going to apply an RF field that's going to start the TIMs, that's going to tip the spins over, start them processing. And as the spins are processing, we want to go into the frame that it's rotating with the spins. And so if we do that, we can derive some equations that look like this. And so the z direction along this direction is the stationary direction. And then I have a prime on these two axes because these are the axes that are rotating with the spin. And then also showing here, delta omega then is the difference in the Larmor precession frequency determined by the static magnetic field subtracted from the frequency of the RF field that we're applying. So sorry, this should, omega RF should be this omega here. And now we're going to include all the decoherence effects in our block equation. That's in our T1 and T2 decoherence rates here. And then also spin exchange comes back in because now we're outside of the surf regime, and so spin exchange is going to be our primary source of decoherence. Okay, and so there's a few different types of magnetometers you can build. One is the MZ magnetometer. And so what you have is your magnetic field along the same direction that your optical pumping axis. Again, you're pumping with circular polarization. You're applying this RF field to drive the spin magnetic resonance. And then if you take a look on a photodetector, and that's given by this polarization in the z direction, this equation here, you'll get the electron spin resonance spectrum here as you change the detuning of the RF relative to the magnetic field Larmor frequency. and so it's historically called MZ because you're looking at the Z component of the magnetization. So I've kind of switched symbols. I tend to use P, but older literature uses M, and that's how these names, MZ, came about. And MX is the other one that I'll show in a minute. And so with the MZ magnetometer, you're trying to polarize into the stretch state to show the kind of energy level picture here. And then your RF is driving transitions between all these energy levels. And so it's distributed in the population out. And because we're distributing throughout the whole manifold, that'll increase the absorption. So if you're here, you have very little absorption. And if you're here with the RF, you get lots of absorption. Okay, one could also make a hyperfine magnetometer. Not as frequently done, but it's also possible to do if you drive the hyperfine transition here. And the signal looks almost exactly the same. And that's because there's a lot of analogy with the atomic clock. You can also think about the dead zones. I mentioned that we needed the optical pumping axis along the magnetic field. What happens when you tip away from that? Well, the signal strength starts to shrink. Now, the measured Larmor spin precession is going to be the same, so it's not like your magnetic field measurement changes. It's just your overall signal size starts to go away. But there's a subtlety to that called heading error. And that's because we have, rather than two states, we have multiple states that we're measuring here. I guess here, we have multiple states that we're measuring. And because of these nonlinear effects from the Bright-Robbie formula, this looks mostly linear as each of these MF states split out here. But if you go in and take the difference between these two states, you'll see a small quadratic correction to all these states. And so that gives you a small error when you're measuring this magnetic field. And from the Bright-Robbie formula, you can derive this quadratic term. And so what happens, say, if you flip the magnetic field or flip the light direction, optical pumping direction, relative to the magnetic field? So if you're pointing in one direction, you'll get most of the population. Now I'm switching back to rubidium here. Most of the population in this state, the 2-2 state. But if you flip the magnetic field relative to the light direction in the other, so they're opposite each other, you'll be pumping into the -2 state. And because of these splittings are slightly different, you will get a distortion to the line shape. And if you increase the magnetic field enough, you'll split apart multiple resonances. And I don't think we'll get around to showing that, but in this apparatus, you can apply a large enough magnetic field where you can, rather than a distorted line shape, you can split all these resonances apart and show multiple different resonances in the atom. Okay, so one way of getting around this heading error issue, this is a commercial MX magnetometer, which I'll talk about next, is that, well, let me point out the parts first. Just like this apparatus over here, we're going to have a cesium lamp rather than a laser. We'll have a collimating lens, a filter, but this guy has a split polarizer that's split down the middle. So they put sigma plus light along this direction on one side of the cell, sigma minus light on the other side of the cell, and then they just collect all the light. And so you get these, so one side of the cell gives you one distorted resonance, the other side gives the other distorted resonance. When you add those together on the photodetector here, you get a more symmetric resonance, and it reduces this heading error in the magnetometer. Okay, the MX magnetometer is up next here, and so that means we're going to be trying to look at the component of the magnetic field not along the optical pumping axis, but orthogonal to that. And so we have a very similar situation. We have the magnetic field and the optical pumping axis co-aligned to the magnetic field. We have a oscillating magnetic RF field that we're applying, but we have a second beam here where we're trying to measure this transverse component of the atomic polarization. And so we're detecting that light, say if we're just doing straight up absorption, which we're doing in this apparatus over here, and detect that on a photodetector as we sweep across the magnetic field, which we should see a resonance that looks like this. So we're going to detect this rapidly oscillating RF field. We're going to detect this rapidly oscillating spin precession of the atoms that is being driven by this RF field, and it'll peak up around the resonance. And if we look in the, so these are the two rotating components of the field, and these are added together in this way to create our oscillating field here. And so here we're looking at the MX magnetometer. We're looking at the X component of the magnetization. That's what MX means. And then if we do lock-in detection at the RF field frequency, we can extract these two different quadratures of the signal, the PX prime and the PY prime. And so when you're making a magnetometer, you always want to find a nice linear slope. And so this is a linear slope discriminator, which we can make a sensitive measurement of the magnetic field with the lock-in amplifier. Okay, so I was showing two beams, but more typically you want to just use a single beam. To do a single beam, you try to orient things so that your circularly polarized light is going 45 degrees to the magnetic field. And so in this representation of the rotating wave approximation, the z-axis is always along the magnetic field, not along the optical pumping axis. And with this single-axis magnetometer, you can do something kind of clever, which is, these spins will spontaneously start to oscillate at the Larmor precession frequency, give you a very small signal. If you amplify that signal and give the appropriate phase shift back to these coils around the device, you can make a self-oscillating magnetometer. So this is kind of like an electron spin maser almost, if you will. And this gives a very nice, simple way to make a magnetometer, the self-oscillating magnetometer. And really nice thing about this device is it gives you a very nice flat frequency response. Okay, so just showing the MX magnetometer again, and I have a little animation here. Let's see, so we have some light coming out, and all right, so a little animation here. So the blue vector is the magnetic field, the red is the circularly polarized light, and the yellow is the atomic polarization. And so if we start the animation, we have our RF field oscillating back and forth, and our spin processing around. And so what I'm trying to show here is the light modulation as the spin processes around the magnetic field. So with a simple photodetector, you can read out essentially the angle of the spin again. That's what you're trying to do with the magnetometer. Okay, so we built a very small magnetometer back at NIST when I was there, and gosh, what was that, 2004, 2005 or so. And so we can get a nice dispersive resonance when we do lock-in detection. And then we can measure some sensitivity. And so just wanted to show the sensitivity here that we got with that small device is around 6 picotesla per root hertz. And here, because the coherence time is a lot shorter due to spin exchange, we have a 1 kilohertz bandwidth. All right. One interesting thing about the single beam dead zone, the dead zone of the single beam MX magnetometer is you get this funky looking signal amplitude plot. So you have a polar dead zone for the magnetometer. So if you're pointing the optical axis perfectly along the z direction, you have no signal. If it's in the equatorial plane, you also have no signal. So you need to have the optical pumping axis 45 degrees to the magnetic field to get the maximum signal. And so when you're using this for Earth's field, you got to make sure you orient your magnetometer correctly to give yourself the maximum signal. Okay, in terms of these scalar magnetometers, again, there's been some really nice work coming out of Princeton showing how you can achieve the very best sensitivity in terms of these scalar magnetometers. And they've been able to demonstrate a scalar measurement with a sensitivity down to 0.5 femtotesla per root hertz. So that's more than 3 orders of magnitude what I was showing with the chip scale magnetometer there. So there's a lot of different configurations to do this. One of the tools they're using to get very good sensitivity is they're multi-passing the probe beam inside the vapor cell, I think in this case like 40 times or so. And so that gives you a much larger polarization rotation signal to really boost up the sensitivity. Okay, quickly mention the radio frequency magnetometer. And so I've been talking about, well, let's go apply an RF magnetic field and we'll measure then the Larmor precession frequency. So we tune the RF frequencies such that it matches the Larmor precession frequency. And that, and once we determine what the Larmor precession frequency is, then we know what the DC magnetic field is. But we can flip this on its head and say we want to measure an RF field, say at 20 kilohertz. Then I can tune this DC magnetic field such that the Larmor frequency is going to be 20 kilohertz. And then when a 20 kilohertz signal comes along, then I'll start to see this precession happening. And once again, this is a really nice way to make a sensitive magnetometer, but not a DC, but up at some frequency that is tuned by the strength of the magnetic field here. And again, just citing all this work coming out of the Romalis group at Princeton. But they were able to show some really good sensitivity. This was actually up at a few hundred kilohertz. They were able to show sensitivity around 2 femtotesla per root hertz. One of the really neat effects in this magnetometer is called light narrowing. And if you can put all your spins in the most highly polarized state into the, say, in rubidium-87, the 2-2 state, spin exchange collisions, because they conserve angular momentum, doesn't really cause decoherence. So if the atoms are highly polarized, a spin exchange collision doesn't cause this flip to the other hyperfine state, and so the atoms after the collision will stay in phase. And so if you can get a high degree of polarization, you can really narrow up the line width. So at zero pumping, so this is the optical pumping rate of the circular polarized pump laser. And at zero, they have a quite broad line width that's dominated by spin exchange. They can start to suppress spin exchange by polarizing the atoms. And you can reach an optimum here. And what's interesting here in this inset here is they can show the spin exchange dominated line width, the light narrowed line width, and then if you go down to zero field to get in the surf regime, you get this little tiny spike here that's showing the line width in the surf regime. So you can kind of explore all these different regimes of line width by playing around with magnetic field, light power, and tune the sensitivity of your magnetometer. With these, with this light narrowing, the minimum decoherence rate you can achieve is basically the geometric mean between the spin exchange rate and the spin destruction rate. And so that's a nice result that they were able to show here. Is how you can minimize the line width in this type of magnetometer. We've also built ourselves a magnetometer, kind of a compact one to take outside, and we're able to achieve about 9 femtotesla per hertz. So it's the sensitivity plot that we got out of our device, along with a calibrating signal here at 21.75 kilohertz. All right, geez, I'm out of time. So let me just finish up with some applications and not go into the spin squeezing and pulse magnetometry. Okay, so some of the applications of magnetometry, we're looking at the, a lot of them are, we're looking at the Earth's magnetic field. So what do you want to do in the Earth's magnetic field? One of the biggest applications has been oil and mineral exploration. Archaeology has also been another big application, and also unexploded ordnance. So we're looking for improvised explosive devices, or IEDs. Other applications are remote sensing. Say if you want to detect vehicles or magnetic objects coming across some border that you don't want people to come across. And magnetic navigation is another big application that's starting to gain a lot of traction. Okay, so just quickly, archaeology. Here's a magnetic survey that was done. And this is, completely invisible on the surface, but you can see this magnetic anomaly here that's from an old stone wall. And then another interesting thing that I came across was like basically 10,000-year-old hearths from people up in Alaska. And so if they've made fires in the same spot over and over again, that raises up the temperature in the ground pretty high, and it demagnetizes the rock in that hearth. And so they can go and find these magnetic anomalies where there's been a hearth pit. And so these are showing some of the anomalies that we're seeing here. And so the scale here is kind of several nanotesla. So it's a pretty small signal, but if you get down close to the ground and sweep across it, you can detect these types of things. Here's another crazy thing called mag and flag. And so if you're doing unexploded ordnance detection, you sweep across a field and try to find all the different little magnetic anomalies. I wish I knew more about this picture, but it's just ridiculous. Like, how do you know where you're going to go dig a hole to try to remove unexploded ordnance? But I got this picture from Geometrics, and I don't know, maybe it's the yellow ones you want to go dig up, but the red ones, or maybe it's the red ones. I hope it's the yellow ones. There's fewer of them. And then finally, I'll mention magnetic navigation. And so there's a lot of concern about how easy it is to jam or spoof GPS. And so what are some alternative ways we can do navigation? And one of those is to measure the magnetic anomaly in the Earth's crust and essentially do map matching. And so say as you fly an airplane across the Earth's crust, there's going to be all these variations in the magnetic field due to different orientations of the rock in the crust. And if you have kind of a preloaded map of the magnetic field in your navigation computer, you can match all these variations in the magnetic field to a particular path, and you can determine your location that way. And so for relatively low altitude flying, people have been able to show that you can get kind of 30-meter or so accuracy by doing this sort of magnetic map matching, as long as you're also have an inertial measurement unit working with it. Okay, and let me end with some references here. Highly recommend this book. There's a great chapter in this book by Peter Schwindt you should go read. And then, yeah, some other general references here. So thank you very much for your attention.
Anybody have any questions for Peter?
Yeah, if I may say, Peter, I've never heard the CERC regime explained so well. Right. So back to the surf regime, I wondered if there's an analogous regime for nuclear spin precession, where spin exchange is otherwise limiting coherence time effect.
I'm not aware of one. I mean, I think usually in nuclear spins, they're kind of locked together, or they're kind of fixed down in in some sort of solid matrix, right? And so I'm not. It may. I don't know. Does anybody else know? I'm not aware of a similar sort of regime like that. But okay.
I don't know, but I'd be surprised because in my field where we have electron and nuclear spins in solid state, to get the nuclear spins to flip, you kind of have to use the electron most of the time.
Yeah.
So
Maybe like the polarized gas people do the spin polarized xenon and helium might have seen something, but I don't know.
Yeah. I mean that's true. There's there's a whole field I didn't talk about here, which is polarizing nuclear spins in noble gases. And so we can spin polarize helium-3 or xenon-129, 131. And, but I haven't seen anything where you kind of, through collisions, you lock these spins together. It's more, there's some interesting work coming out of Berkeley and Ashoka Joy's group where he's playing some interesting tricks with nuclear spins in NV-centered diamond materials. And he can demonstrate very long coherence time by doing the appropriate rotations of the nuclear spins to maintain their coherence. But I haven't really digested that to really understand what that is.
I have probably a naive question because I'm not so much in this field. But the temperature dependence part, as far as I understood, in the block equation, the only parts where the temperature enters is in the diffusion term. But so I can see that in gas phase, but I don't know how you do that when you have solid state or any other, the brain situation that you described.
Up next is Andy. He'll be in the solid state. He can talk about temperature. Yeah.
Because the temperature effect seems to be extremely important. And it doesn't enter in the quantum equation as such, but of course it enters in the Liouville equation.
Yeah, so let me trying to get back to that slide. So the temperature effects are mainly the density of the atoms. So the density, so as you raise the temperature, that increases the number density inside the vapor cell, but they're still in the gas phase. And so the way they interact is through collisions, right? And so the way the temperature comes in is through the collisions. Yeah. Jeez, I could answer the question before I could find the slide. But yeah. I mean, so the temperature here, temperature comes in as the number density of potassium here, right? And so what that is, the main effect then is coming in here. So we have some temperature effect in the alkali buffer gas collisions, and then there's a strong temperature effect in the number density of rubidium. So that's really bumping up the collision rate, right? Yeah.
Spin destruction is loss of coherence. Is that what it is?
What is spin destruction? Yeah, I didn't explain that very well, but spin destruction is basically a randomization, non-angular momentum conserving collision that randomizes the orientation of the electron spin. Yeah. And so there's a lot of study on what the Hamiltonian and the dynamics of these collisions are, but it's kind of beyond the scope of what I actually know and what I want to go into. So yeah. For me as a user, I just kind of take that rate and calculate it and to calculate the sensitivity of the magnetometer.
Okay. So regarding the temperature, so rubidium base, I think it's a solid at the most of the room temperature. So probably we need some heating to have enough vapor.
Yeah.
And then in the system, like let's say you have some kind of a temperature gradient. Does that affect the sensitivity of the system?
If you have a large enough temperature gradient, you can get a temperature gradient of the vapor across the cell. Generally, we try to maintain that gradient kind of less than 10-ish to 10, 20 degrees. At that level, you can kind of just say, the density's uniform throughout. And so don't typically see that sort of effect. But if you do have a really strong temperature gradient, that is a measurable effect.
Hi. So I think on one of your maybe 75% of the way through, there was magnetic field that was like vibration sensitive, right around like 100 hertz or something from the table vibrations. Like, what is the coupling mechanism for that? Is it like the vapor cell compared to the surface of the table, or is it like compared to the
that's
or the optics
yeah,
mounts?
good speculation, but so we're bringing light in from fiber-coupled sensors, and so that really comes in through the light. And so our laser system on this table that's vibrating is essentially changing the amount of light getting to the sensor. So the amount of light getting coupled into the fiber that goes to the sensor. Another vibration coupling mechanism is we use a polarization maintaining fiber, but if we vibrate that fiber enough, we can see a change in polarization as the light propagates through that fiber. So there's a lot of different ways that vibration enters through the optical system that's feeding the magnetometer's light. Yeah. Yeah. I mean, there's all sorts of ways to make vibration kill you. You know, say if your table's vibrating and vibrates your magnetic shield that you're doing the measurement in, that will also give a vibration effect. Yeah.
All right. If there's no more questions, let's thank Peter once again. We'll take a quick 10, and then we'll come back and hear from Andy.